Hi, welcome back to my channel. Today we're going to introduce the concept of mutability in the Racket programming language. Now what mutability is that it's just in the notion that a lot of people are probably already aware of, that when I'm in a traditional programming language, I can do things like set a value like an integer, a variable like I, give it an initial value, and later on mutate it or just basically change its value to be something than it was when it was initially created. So I can go and say something like I equals I plus 4. It's very simple, straightforward. But as you may have noticed in the programs that we've done in this talk so far, that we have never really done statements like that, ever. What we've done is we've done things in the functional style, which is we have functions that return new values, and then we operate on those new values. So for example, when we are working with a list or doing certain things on a list, we don't change that list and mutate it to be a new value. We actually create new values by returning it from a function. And there is a lot you can do in that model, and that model is actually very, very useful. And one might ask, it's like, well, why do functional programming languages try to avoid that as much as possible? And we'll get back to that. But the other thing about it is that, why, do we actually need to do those things like mutability? And the simple answer is that technically, no. You can get away with having a Turing complete. And what Turing complete means is that it basically can do the basic, whatever can be computed can be done by a Turing complete language. However, just being Turing complete does not necessarily mean that language is very practical. And if you look at the vast majority of problems that programs trying to solve, those actually do things like want to mutate state or actually make a change in the world around them. For example, I don't go to Amazon to merely just put a bunch of items in a shopping cart and see how much they would cost. The goal of this is to actually have it so that there is a change in state in which those items are then sent to me at a certain address, and then I am billed for the cost of those items. And if you go off to my bank, again, it'd be one of those things where I would not go to my bank and just say, well, I would very much like to go off and have this thing where I just want to see how much money I could add and subtract to a bank balance. That would make no sense whatever. I want to be able to deposit and withdraw certain types of things. And also I want to see that history of deposits and withdrawals to understand how I'm spending my money or saving my money. And doing that in a pure functional way where every transaction on a bank account returns an entirely new bank account frequently becomes very unwieldy. And of course, is not how you would do things in the real world. And so the vast majority of systems that programs interact with do have a mutation of state. And it's not only a mutation of state in terms of the program itself, but also a mutation of state and the world around it. So, of course, Racket, like all other programming languages, really do have some notion of how to do mutation. And Racket does things a little bit differently for those of you that are more familiar with Scheme and Lisp, in the fact that lists in Scheme and Lisp are mutable, and there's certain operations that allows you to change values inside a list. But Racket uses a mutable list by default, and there's some very, very good reasons for that. And so that caught me up when I was doing the first version of this, when I was trying to run things, when I had my old understanding of Scheme, and that caught me off guard. And so I realized, oh, wait a minute, they have something different. And what they use is a notion of a box. And a box is kind of an idea that was kind of borrowed from object-oriented languages in terms of an operation that takes primitives and hoists them up to an object perspective, or unboxes them, moves them down to a primitive, and how certain runtime environments could do that automatically. C# is kind of famous for this, where they do a lot of operations where they automatically box and unbox things as necessary to keep the type system a little bit more aligned with certain features. So that's what we're going to use here to create a stack. And a stack is just this basic idea of, I have things like I put books on a shelf, put books on a desk, and and I stack them on top of each other. And then when I pop is literally just like taking the book on the top and returning it. And so that's what we're going to do here. So I've defined a stack new, and I've created a box which contains a list, an empty list. And it turns out, in this case, lists are perfect for implementing stacks. There's probably no better implementation in terms of efficiency than a list. And we'll kind of see why in a second when we talk about the basic operations of push and pop. So the design stack push, we're given a stack, and we're going to get a value that we want to push on there. First, we're going to do is I want to get the value of the underlying list that's inside that box. So I unbox the stack, and then I go off and set the value of that box. That's what set box does. It says take this box, set it to have this value. And this value is now just the value cons onto that list, or just stuck onto the beginning of the list. Now I have stack pop. Stack pop is very similar. I'm going to get the list by unboxing that stack. Then I'm going to do a quick check here. If the list is empty, that inside this box is empty, there's nothing in that stack, I'm going to throw an error. And the reason I throw an error is that I don't want to return just an empty value, because an empty value is something that should be able to be pushed onto a stack. So I want this to be an invalid operation depending on the state of that stack. If the stack is empty, then this is an invalid operation. Otherwise, I want to do the following, which is basically first, before I do anything, is I want to get the first value of that list, set it to V, and then I'm doing two things here, and let allows me to do multiple statements, or multiple statements, in Scheme. The first thing it does, it says, I want to set this box, the stack, the value of this box to just be the rest of the list, and then return that value, which is the first one on the list. Now, as an exercise for you, I will go ahead and say, how would you define stack as empty? Should be fairly straightforward from these two, but it's a good exercise for the viewer to implement. So now what I'm going to do is I'm just going to do some basic tests here. Just basic subsanity checks. I'm going to define a test stack, which is whatever this, make a new one, call it test stack, push on 4 and 3, and then see what pops off. Going to go run it. And, it's complained about this, so I'm going to go ahead and comment that out, because, of course, would actually need to provide that body. And lo and behold, it returns 3. And you can see that if I added another call here, stack pop, that it would actually return 4. The first thing I want to point out is that you may have noticed these exclamation points here. These are a convention in Racket, such that anything that mutates something that is passed to it here, in this case, the stack itself is being mutated. Anything that mutates a value that's being put into it should have this exclamation point behind it. It's not enforced. It's just a convention. Same way that if something ends with a question mark, it is considered to be a predicate that returns a Boolean, which is basically, something that returns true or false. But then again, that is not enforced by the language. So it's just a convention that's very, very useful. And a lot of people look at it to make sure that they understand, this is what this is doing. Now, there's the thing about that. What makes this very interesting, and I won't go into it because we're going to go into each aspect of this differently, is that having these concepts of mutability, while being very important in terms of managing certain types of practical programming problems, adds an order of complexity to reasoning about programs. And the amount of complexity that they add, when you take into account all the dimensions that are available to us, is actually why modern programming is so difficult. Functional programming, there's quite a bit of difficulty to reason about the functions that take a certain amount of information from one domain and transfer it to a certain amount of information from another domain. There's a lot of business logic problems that really are about that are really those transformational functions. But there's also a lot of business logic that is based on that state. And now the first thing that we have to deal with when we add state or mutability to the equation is that now we have to care about the order in which things have happened. And that adds a whole other dimension of complexity to understanding what a program does. And the reason being is that there's just this whole new dimension that we've added to it. And that just really just kind of blows up the entire solution space, sometimes to a very, very large degree. And if you can think about it, modern programming languages and things like object-oriented programming, modern functional and object-oriented programming languages, and the hybrid of those two really have come up with just newer and hopefully more useful ways of maintaining that state in a way that's more manageable than just an arbitrary set of functions on an arbitrary set of data that can be implemented in an arbitrary order. And so if you think about it, that's fundamentally why object-oriented programming was kind of invented, was to have a way of hiding certain amount of state behind a set of abstractions, such that it would be harder, if not just almost impossible, to manipulate that internal state without using things like, reflection and all sorts of very complicated things. And functional programming languages also went around by trying to do things in an immutable fashion and then pushing out the state parts to their own types of things. Now, I won't get into how Haskell or F# manages this until much later in the series, but just know that they also deal with state and state transformation and do have mutability, but the way that they deal with it can often be confusing to someone who's just used to C programming. And the reason being is that in that domain, they are trying to preserve the ability to reason about those programs as much as possible by enforcing a set of abstractions that may seem fairly confusing at first. And if you don't understand that what the goal is to be able to reason about these programs better, then adding all the abstractions that they have for managing state just almost doesn't make any sense. And for a certain set of programmers, it almost becomes just like completely baffling and makes no sense, and becomes very difficult to explain. And Racket is kind of in between those languages. It definitely is functional, and it definitely tries to avoid mutability. But it provides a little bit different set of primitives that are a little bit easier to deal with than some of the other, what you would maybe call pure, some people would call pure object functional programming languages like Haskell. So that's what we'll get into here. And I'll stop with that. Because if I get too much more into the additional details, this could be a very, very long video. So again, the other thing about this is that I want to point out is that one of the good exercises to go through, you note, is I had to use this box type of thing. One of the things that you could do is you could go off and just rewrite these things, but just pass in a list instead of this stack and see what happens, right? So you don't have to do this unboxing and stuff like that. And you'll note that it won't work as you expect. And the reason being behind that is that, and we will get into this when we learn about how, programming languages fundamentally work and how you can reason about them in terms of things like metaprogramming. But just for now, what you should know is that when you call functions in Racket, it is called by value. And what that means is that if I pass in a variable to a function, like my function, and I pass in some thing to it, it will make a copy of something. So anything I do to something here, like consing it, doing whatever with it, or doing sets and whatever, will happen to that copy. It will not be passed on to the outside world. And that's the call by value parameter types of things. Again, in the next video, I will get into a little bit more about calling conventions and how they affect programming languages. But for now, just be aware of the fact that just because you pass in a value into a function, by default, it's not going to try to do and change that value. And again, that comes down to a reasoning type of thing. It's there's a term of unexpected consequences when that happens, but basically it's kind of annoying, that programming model, unless you really understand it, when it's really well documented, to know that, oh, by the way, when you pass in certain types of things, it will willy-nilly change them. So anyway, thanks for watching, and I hope to see you in the next video.